Good morning, afternoon, or evening, depending on where you're watching from. My name is Kevin Hitt, and thank you for joining today for my predictive analytics presentation on predicting income. The objectives for this project will be to determine whether income exceeds $50,000 or not annually. This will be accomplished by building a predictive model based on 1994 census data. I'm going to approach this from two angles. First, using traditional statistics, and secondly, using machine learning approaches. Before diving into how we approach this objective, let's set it in context by first looking at the data. This data was sourced from University of California, Irvine, Machine Learning and Intelligence Systems. It's a data set based on a project with the prediction task of determining whether a person makes over $50,000 a year, and has been accessed over 2 million times since it was first published. It is notable that this data was collected, or rather published, in 1994. And given certain considerations, such as inflation, any interpretation we take from these models created may have different implications in today's context. For instance, the Bureau of Labor and Statistics estimates that $50,000 from 1994 would be worth somewhere around $87,000 in today's money. Taking a closer look at the data, here we have an overview of the 9 variables remaining after I had filtered some out. The outcome variable being focused on is income. Other variables are demographic attributes such as age, occupation, education level, gender, and race. Some variables were removed from this analysis. This helps to limit the ultimate size of the data and reduce the chances of the results being skewed by unimportant features or by abnormally distributed variables. For instance, capital gain and capital loss each were not present for 92% of all of the records. Having all of these rows with no information for capital gain or loss could skew the results. Some variables were repeated, such as education and education num, and other variables were not self-explanatory, like final weight, so that was omitted. Others, like relationship, were duplicative in the sense that they could be interpreted from other existing variables, such as gender and marital status, predicting a relationship. To help the model even further, some of these existing 9 variables were grouped semantically depending on their factor levels. This will help to reduce noise when interpreting the different factor levels for each of the variables. So for instance, the occupations list was broken down and grouped into 6 categories of white collar, blue collar, professionals, sales, service, and unknown. Broadening the labels here allows the model to more effectively see relationships as opposed to having it so granular that it doesn't lead to conducive results. So this condensing of the format broadens it to assist the model, but keeps it specific enough to when we interpret the results, we can still pull something valuable from it. Now that we've seen our objective and the data that we're working with, we can break down the methods that we'll use to build these models. They both will follow the lines of supervised learning. The first is the traditional statistic method of logistic regression, and then the second is the machine learning concept, random forest. These steps are then followed by cross-validation. Supervised learning methods were chosen because we already have our target variable of income, and we already know that that is what we're trying to predict relationships for among the other variables. Unsupervised learning might help us discover new or novel trends between other variables, but our focus and the objective of this project has been narrowed down to income. Logistic regression is used as opposed to linear regression because the income value is not a continuous variable or dollar amount, rather it's just a categorical value indicating whether someone is or is not making at least $50,000. A multivariate approach is used in combination with this because we'll see that implementing a higher number of variables can often lead to better prediction results as opposed to just a hand-chosen few. Random forests will also be implemented as another supervised learning approach, and this will offer a good base for comparison to compare with the logistic regression model. Finally, cross-validation is used, tenfold cross-validation, and this evaluates the performance of each model to see whether we're overfitting them with the training data that we use. Here we can see 5 rows of results, the first 3 for logistic regression models and the last 2 for the random forest. As they are listed, they increase in complexity, seeing that the first logistic regression model only considers 2 variables outside of income, and the second regression considers 3, before the final one considers all of the variables. That same pattern follows for random forest. And we can see from both the tenfold validation accuracy result and the prediction accuracy on the test set after the training that the accuracy seems to increase as more variables from the total 9 are considered. Cross-validation wasn't used for the random forest models as it's not needed for a separate test to get an unbiased estimate of the test set error since it's estimated internally during the run. Taking a more specific look at the highest ranked model, the third logistic regression model, we see the area under the curve graph here, illustrating its 87% we saw earlier. I've also included the model output here on the right and highlighted some of the more significant values as indicated in the red boxes for the p-score column. The estimate column also gives us some good revelations, as we can see here most dramatically within the group of marital status. The factor level that is omitted here is divorced, so that we can see now when we look at the listed value for married, that large positive number 1.94 indicates that in comparison to divorced individuals, married individuals seem to more often than not make more than $50,000 according to this data. Similarly for white collar versus blue collar workers. Now that we have established our objective, reviewed the data, made a plan to develop the models, created them, and evaluated their performance, we can see that traditional statistic modeling techniques like logistic regression, while traditional, should not be automatically substituted with newer technologies like machine learning concepts such as random forest without proper consideration. While machine learning techniques are undeniably powerful, we can see here from the logistic regression models that for this specific case, they also perform just as well, if not marginally better. The most interesting findings I see from this analysis relate to the third logistic regression model's list of variables that were most correlated to income, such as age and working white collar or blue collar. However, as we can see from the visual here on the right, there are some inherent biases with the data. Not only are slightly more than 3/4 of all records for individuals that make less than $50,000, slightly more than 2/3 of the data are also made up of only males. While there may have been some inherent biases in the census survey, we have indications that this is not a true reflection or good snapshot for what we would expect from a census. Another possible issue with data quality was in the data cleaning step. Should we have merged all of those categories, such as for occupation and marital status, or if we had left that higher number of categories indicating more specifically the status of marriage and their type of occupation, would that have helped our results or hindered them like we assumed they would? Likewise, for some variables omitted that we assumed would not have any relevance, could they have played a role, such as the native country variable that we omitted? Overall, we've accomplished our objectives of building the predictive model from 1994 census data that allows us to predict whether income will be greater than $50,000 with around 80% accuracy. That was my presentation, and thank you for your time. Have a great day.